Hi again, this is Claudio from expertfea.com, recording the third webinar meant to help you improve your finite element analysis and Ansys Workbench skills. Firstly, we invite you to access our webpage, which is updated very often, to check out our tutorials, our gallery with solved FEA cases, our book with hints, and the webinars we record and post on YouTube. Also, this is our YouTube channel, which is very rich in FEA solved scenarios. So, for today, we are going to perform a transient structural FEA of a crank and slider mechanism. Let's import the needed geometry. And access the mechanical window. I am often asked what is the difference between static structural and a transient structural. The main difference is that in this kind of FEA the time has sense, meaning that we can trust and find out velocity and acceleration as output. This is not the case in the static structural FEA, where time is only a division, let's say, of the boundary condition. It's only useful to define the time steps, let's say. So, by default, Ansys assigns contacts . In this case, we don't need them, so we can right-click and delete them. This will be the driving part of the whole assembly, meaning that we will assign a Revolute joint on this surface. This part will be, let's say, the fixed part, meaning that we will assign a fixed joint here, which is created automatically if we select the surface and click the fixed button. So, the movement will be propagated to this part, so from this part to this part. This meaning we need a Revolute joint between these two parts. Be sure to check the body tab and select the Revolute joint. Let's zoom in a little, and for reference we will select the inside of this part, and for mobile we will select the outside of the other part. If you'd like to clearly see the mating parts, you can also click the body views button, and here is it's more easy to understand the mating parts, let's say. So the movement is propagated to this other part. This meaning we will need to define a translational joint between this face as a reference and the touching face as a mobile. this part will then mate with this fixed part. This meaning we need to define again a translational joint, choosing this surface as a reference and this surface as mobile. Let's define here 4 steps. We will select with shift pressed all the 4 steps and assign here 0.2 seconds, 0.1 and 0.3 seconds. We will also click carry over time step on, even though it's not shown because also the first step is selected. When we click on them separately, it will be shown carry over time step. Alright, so what we need is a joint load where we will define the rotation of this part. Type will be rotation and the magnitude will be inserted in a tabular data. Let's write here 90 degrees and in the end 360 degrees. You observe that Ansys automatically fills up these values, which is very good. So let's ask for deformation, total, directional velocity, directional acceleration, total strain, stress, a joint probe, let's see, in this body and body joint we need a total force. Alright, this is pretty much all. Now we need to solve the FEA. This is the mesh, which is pretty coarse, let's say. We get a wording. We can double click it, copying the source mesh, preview after your sized. Please try to generate volume wash again. We can just delete it. Let's click on solution information and see what the solver is doing. So the analysis converges very well. We can, let's see, clarify the display points. Insert here 35. And we see that the FEA does not fully converge. Let's see why. 50 frames, 5 seconds, play. Yes. What happens here is that I forgot to correctly place the x-axis for these joints. So what we see here is that we know that the direction is on the y-axis, the direction of the movement, but the joint is defaultly defined on the x-axis. So we need to switch somehow the x-axis with y-axis. It's very simple to do it by clicking Reference Coordinate System, and instead of geometry selection here, we will choose Global Y-axis. So now we see that is what we needed, that the movement will happen on the x-axis. Let's do the same for the other translational joint. The x-axis should be in the direction of the global x-axis. So let's solve again. The FEA converges very well. Let's look on the time increment plot. It's shown the minimum time step we assigned. And again, the FEA fails. So let's see what happens. On the maximum height, it blocks, let's say. This is solved very easily if we select all the joints and make them their behavior as deformable. So let's solve again. Later on, for all these items, we will scope only certain parts and not the entire assembly. We can delete this, warnings, and now we see that the FEA fully converges to the end. The end meaning the fourth second, where we have a full rotation performed. So now it's successfully solved. let's run a little animation. Everything goes perfectly. Alright, let's clear generated data, and for example let's select only this part on Y global axis. Let's see also its velocity. On the same y-axis. Also the acceleration on another part. Let's say this part. On x-axis. We leave it like this. Let's check the strain on this part. The stress on the driving part, and the joint probe, we leave it like this. Moreover, what we can do is, if we have solution selected, we can click the worksheet button and choose more items to show. Let's say we need the angular velocity in all the parts. And we're interested in finding the angle of some parts. So let's right click solution, evaluate our results. Browsing again through the results. We see the directional displacement of this part. It's rectilinear velocity, 100 millimeters per second. The acceleration of this part, total strain on this part, the stress on the driving part. The values are very good. The total force on this joint. We see that it changes the direction while moving. The rotational velocity in the assembly. Maximum is 3 radian per second. And the angle of these parts. We see that we go almost to 180 degrees. As it is expected. Moreover, what we can do is, if some parts are not of interest for us, we can make them rigid, meaning we'll have a let's say smaller number of nodes. Let's say that we'll make this part rigid, stiffness behavior rigid, and the last part, the fixed part, again rigid. Let's solve the FEA again. The mesh, as you would expect, has a lower number of nodes and elements, and the rigid parts are not meshed. In the solution information, we see that it converges very fast. Until we reach the solution, of course, that you can refine the mesh according to your needs. But for this case, we are satisfied with what we see. So, the FEA is solved, and we get similar results as before. So, this is the third webinar. We invite you to make your own simulation according to what you have seen in this webinar, and wish you best of luck in your FEA practice and in life. Goodbye.